Let me explain how the second half works. Suppose our actual robot sits over here, and it measures these exact distances to the landmarks over here. Obviously, there's some measurement noise that we just model as an added Gaussian with zero mean, meaning that we have a certain chance of being too short or too long, and that probability is governed by a Gaussian. So this process gives us a measurement vector of 4 values of those 4 distances to the landmarks L1 to L4. Now let's consider a particle that hypothesizes the robot coordinates are over here and not over here, and it also hypothesizes a different heading direction. We can then take the measurement vector and apply it to this particle. Obviously, this would be a very poor measurement vector for this specific particle over here. In particular, the measurement vector we would have expected looks more like this. That just makes this specific location really unlikely. In fact, the closer our particle to the correct position, the more likely will be the set of measurements given that position. And now here comes the big trick in particle filters. The mismatch of the actual measurement and the predicted measurement leads to a so-called importance weight that tells us how important that specific particle is. The larger the weight, the more important it is. When we now have many, many different particles and a specific measurement, each of these particles will have a different weight. Some look very plausible, others might look very implausible, as indicated by the size of the circles over here. We now let these particles survive somewhat at random, but the probability of survival will be proportional to their weights. So something has a very big weight like this guy over here will survive at a higher proportion than someone with a really small weight over here. Which means after what's called resampling, which is just a technical term for randomly drawing n new particles from these old ones with replacement in proportion to their importance weight. After that resampling phase, those guys over here very likely live on, in fact many, many times, whereas those guys over here likely have died out. And that's exactly what happened in our movie in the beginning when we looked at localization in this corridor environment. The particles that were very consistent with the sensor measurement survive with a higher probability, and the ones with lower importance weight tended to die out. So we get the fact that the particles cluster around regions of high posterior probability. That is really cool, and all we have to do is we have to implement a method for assigning importance weights, and that is of course related to the likelihood of a measurement, as we will find out, and we have to implement a method for resampling that grabs particles in proportion to those weights. So let's just do this. So let me add back the robot code. We build a robot and we make the robot move, and we now get a sensor measurement for that specific robot using the sense function. So let's just print this out. These are the ranges or distances to the 4 landmarks, and by adding a print my robot statement, we can also figure out where the robot is as 33, 48, 0.5. Obviously, this is a random output because we randomly initialized the position of the robot. What I want you to program now is a way to assign importance weights to each of the particles in here. I want you to make a list of 1000 elements, where each element in the list contains a number. So this number is proportional to how important that particle is. And to make things easier, I coded for you a function in the class robot called measurement probability. This function accepts a single parameter, the measurement vector, the z I just defined, and it calculates as an output how likely this measurement is. And it uses effectively a Gaussian that measures how far away the predicted measurements would be from the actual measurements. You can dive into this code, understand what's going on. There's one last change we have to do to make this code run. We have to actually assume that there's measurement noise. If there's 0 measurement noise, then this function will end up dividing by 0. So let's put in a clause that specifies what we believe the actual measurement noise is. And I'm going to do this not for the robot, but I'll do this for the particles. In this line of code over here, where we create the particles for the first time, I not just initialize these positions with random numbers, but also assume a certain amount of noise that goes with each particle. 0.05 for the translational noise, 0.05 for the rotational noise, and 5.0 for the measurement noise in those ranges. So this is the crucial number over here. So coming back to what I want you to do, I wish you to construct a list of 1,000 elements in W so that each number in this vector reflects the output of the function measurement prob applied to the measurement Z that we receive from the real robot. Such that when I hit print W, I actually get a list of 1,000 importance weights.